Hey guys, welcome back to another video and another series. In this series, I'm going to be covering analytical chemistry, that is of A2 level chemistry. And in this video, the first video, I'm going to be covering both types of NMR spectroscopy, that is proton NMR spectroscopy and carbon-13 NMR spectroscopy. Note one thing, that in both cases, the process is the same. We're working with nuclear magnetic resonance. The logic or the fundamental behind both the process is exactly the same. So I'm going to cover the process under the topic of proton NMR spectroscopy. Then I'm going to move on to carbon-13 NMR spectroscopy, where the only difference is going to be how we analyze the organic compound. In case of carbon-13, we focus on the nuclei of carbon-13. In case of proton NMR, we focus on the nuclei of the proton, the hydrogen itself, right? So this proton NMR spectroscopy, starting off, it is also known as hydrogen atom NMR spectroscopy because we are observing the nature of the nuclei of the hydrogen atom, right? So what is spectroscopy? Now, to understand spectroscopy, it is defined as a process where the interaction of light with matter is observed. So in this case, in our case, what is the matter we are analyzing? We are analyzing organic compounds, right? We are trying to identify what organic compound we have using nuclear magnetic resonance. So spectroscopy is basically telling you as a process where you're interacting that organic compound with, let's say, any sort of electromagnetic wave and seeing how that organic compound is going to behave under the influence of that electromagnetic wave. So, spectroscopy is a process where the interaction of that matter and EM wave is observed. How it's going to behave. That is the fundamental process of how NMR really works, how the organic compound is going to behave upon the interaction of any, in this case, we are going to be using radio waves because that is going to affect our organic compound. We're going to understand in details how it really happens. But anyways, as mentioned before, both carbon-13 and proton NMR works under the same process. Now, in both cases, we're going to be observing the nuclei of the atom, that is, of the hydrogen atom and the carbon-13 atom. Great. Now we're going to see that the nuclei which contains the proton and neutron, in case of hydrogen atom, only the proton. In case of carbon-13 atom, it contains protons and neutrons. Now what we're going to observe is the nuclei actually is going to behave like magnets. Why is it going to behave like magnets? Now we're going to understand that over here. So basically what happens is, let's say, since talking about proton NMR spectroscopy, we're going to observe the nature of hydrogen atoms. Right. In case of a hydrogen atom, what do you have? An electron orbiting around this blue cloud. And you have in the nucleus a proton spinning. This is an important part of this entire topic. The proton is spinning. Now, which direction will it spin? Any direction. So if you have 100 hydrogen atoms, each of the nuclei is going to spin either clockwise or anti-clockwise. Now what happens is, let's say one is spinning clockwise, right? In that case, it's going to create a magnetic field, let's say upwards. Because you already know from magnetic fields that if a charge moves with a velocity in any direction, it's going to create its own magnetic field. Similarly, if it's spinning, let's say clockwise, it creates a magnetic field upwards. If it's spinning anti-clockwise, it's going to create a magnetic field, let's say downwards. So depending on the spin, the direction of the magnetic field is going to change, right? So the spin is a property giving rise to the magnetic behavior of the nuclei of the hydrogen atom. Great. So let's understand in steps what is happening again. The nuclei gives the magnetic property. Right. The nuclei gives the magnetic property. Fair enough. The nuclei contains one proton that can spin clockwise or anticlockwise as seen over here. Right. This spin gives the magnetic property of the hydrogen atom. Due to its spin, it's going to create its own magnetic field. Now, normally, when you have a bunch of hydrogen atoms under no influence of external magnetic field, it's going to be in, let's say, even proportion of clockwise spin and anti-clockwise spin. So let's say a bunch of hydrogen atoms are spinning clockwise, the rest is going to spin anti-clockwise. So there is no definite way to distinguish which is spinning clockwise and which is spinning anti-clockwise. However, this is an important attribute of the hydrogen atom. Why? We'll see in a moment. So until and unless you have external magnetic field applied, both are going to spin on its own direction. One will spin clockwise, one will spin anti-clockwise. There's nothing stopping them from spinning in its own direction. So the spin of the nuclei makes the hydrogen atom act like small domains of a magnet. That is, one is, let's say, creating a magnetic field upwards, the other is creating a magnetic field downwards, just like a domain, which directs either upwards or downwards depending on the external magnetic field. Here is where the external magnetic field comes into play. So first off, let's understand with a diagram how the magnetic field direction is defined. So let's say you have one spinning clockwise, that is this one, and you have another spinning anti-clockwise, right? Now in case of the one spinning clockwise, what you have over here is, if you use the right hand grip rule in general, you're going to see that north is facing downwards, so it's going to create a magnetic field moving from this direction to this direction to this. So what this creates is a magnetic field upwards. Similarly, you have one spinning anti-clockwise. Now if you use your right hand grip rule, what you're going to see is, since it's moving anti-clockwise, the north points up, so the magnetic field is directed downwards. Right. Now assume this is how the magnetic field of the spin of the nucleus is defined. So when it's spinning clockwise, it's going to be facing north downwards, so the magnetic field is this way, and for this way. So now taking that notation, if we move on to bringing in an external magnetic field, we're going to see a new phenomena that's going to happen. What is going to happen? Now, let's say we apply an external magnetic field. Now, in the presence of both of these spins, what's going to happen is one of the spin is going to align with the external magnetic field. That is, since this one is spinning clockwise, it creates a magnetic field upwards, let's say. And this direction of the magnetic field aligns with your applied magnetic field, which is this one. It aligns, right? However, notice the other one that is spinning anti-clockwise, what's happening is its direction of magnetic field is downwards, which does not align. Okay. Now, okay. So one is going to align and the other is not going to. Fair enough. Now, the proton whose magnetic field aligns with the applied magnetic field is going to be stable. Why is it going to be stable? Because it's going with the flow of the external magnetic field. It is not resisting the applied magnetic field. It is in the same direction as the applied magnetic field, which is why it is stable. It doesn't have to resist anything. This is also the reason why it has less energy, because it has nothing to resist against. So it has less energy, more stable. Great. Now the other fellow, which is spinning anti-clockwise and has a magnetic field in the opposite direction, is going to be unstable. Why? Because it's resisting against the applied magnetic field. I'm giving a magnetic field that is upwards, right? However, this is resisting that change. It is going against my magnetic field. which is why it's going to be unstable, which is also why it's going to have greater energy, because it has to resist my applied magnetic field. Great. So this is why, what do we understand? One is going to be stable, less energy. Unstable, this one is going to be unstable, greater energy. Great. So we have two types of hydrogen atoms under the influence of external magnetic field. Fair enough. Okay. So now the moment you have applied a magnetic field, what's going to happen is some of the nuclei is not going to continue to resist that applied magnetic field. What it's going to do is it's going to align itself, it's going to change its spin, hence flip. It's going to flip its direction and it's going to align with the external magnetic field. So the protons will change their spin. So a few of this type of spins is going to change its direction. And what's going to happen is it's going to align with the external magnetic field. However, many will not. Some will remain and continue spinning in the opposite direction and resist the change and will remain in an unstable greater energy state. So we have two types of spin under the influence of external magnetic field, one stable, one unstable. Great. Now, due to this disparity between the spins in the presence of a magnetic field, we're left with hydrogen atom nuclei that are in different energy levels. This is the important part. Some of the hydrogen atoms, the nuclei of it, is going to be stable, less energy, so on a lower energy level. The others, which did not align, did not change its spin, is going to be resisting the external magnetic field, hence is going to be unstable and is also going to have higher amount of energy. Because it's moving against. So notice one thing, both of these are going to have a del E value. What does that mean? It's going to have a difference in energy level, meaning this one has more energy than this one. So what you can predict from this is if you apply or transfer enough energy to this aligned proton, it's going to gain that energy and start moving in the opposite direction, that is anti-clockwise, and become unstable. The moment you provide this del E energy to this proton, it's going to go against the magnetic field and start moving in the opposite direction. Now this del E value you can probably relate from either transition elements, where we talk about providing the exact amount of energy and exciting the electrons, or in some cases the electrons de-excite, and there is a difference in energy level and there's a difference in energy value, del E. And this concept also is present in quantum physics in A2 level. So what this is denoting is, if you apply this exact amount of energy to this aligned proton, it's going to change its spin and go against the external magnetic field. Great. So understand that between the two energy levels, there is a difference of energy, that is del E. That is, if I provide the stable nuclei with exactly the del E energy, then the nuclei will flip its spin and is going to align against the magnetic field. So understand that the moment one is changing its spin, it is called flipping. It's going to flip its direction from, let's say, down direction to up direction. That is called flipping, right? It's going to change its spin to not align with the external magnetic field. Now, this flipping is called resonance. If flipping has happened, if this proton has changed its direction of spin, it has flipped. Therefore, you have achieved resonance. Now, notice one thing. if you keep the magnetic field strength constant, let's say 1 Tesla, if you keep that magnetic field constant and you apply, let's say, external energy, how can you apply external energy? Through EM waves. You can shoot a bit of EM radiation. What sort of EM radiation, you ask? Radio waves. If you apply a bit of radio wave, what's going to happen is that radio wave is going to transfer energy, to the aligned proton and is going to change its spin. However, it has to exactly provide this del E value. Right, so granted we keep the magnetic field constant, we can provide the exact energy to the nuclei using radio waves. Using what? Radio waves. Okay. Now understand that you need to exactly provide the del E value. Now, if you remember from, if you've studied quantum physics or from transition element, there is a specific frequency for which this del E value can be achieved. That is, the formula of this del E is going to be Planck's constant times frequency. What is this frequency? This is the frequency of the radio wave which exactly provides the del E value. So the moment you have a radio wave frequency matching this frequency, that is going to be your resonance frequency. And that is going to be the instant that the protons start flipping. They change their direction of spin. So this is when resonance occurs. And that is also when on the spectra, on the NMR spectra, you're going to see spikes. The moment the spins change its direction, it's going to show a spike on the NMR spectra. That means at that frequency, your hydrogen atom, the nuclei of it, has changed its spin. That is the resonant frequency. Great. So now we understand how the spikes are happening, why the spikes are happening, why we see the spikes on the NMR spectra. So when we provide the exact frequency, when you're applying the, radio wave while there is a magnetic field, so you're providing both the magnetic field and you're applying radio waves. Why? To give the energy, right? So when you're applying the radio wave, you're applying a range of frequencies, right? So when you're applying the radio wave, there's a range of frequency. The one that is going to be exactly giving the del E value is going to convert or flip the proton, right? So that is again the resonance frequency, and that is when you see the spike on the graph. Okay, so when we provide the exact frequency, we see a peak in the NMR spectra. Great. Now, the interesting part is over here again. The hydrogen atom in different environment is going to have different del E value. What does that mean? So if you have any compound, let's say and hydrogen over here and hydrogen over here, notice this hydrogen atom is in a different environment. How so? It's connected to one carbon atom, and nearby it there is two consecutive carbon atoms. Now notice this hydrogen atom, this is near two carbon atoms but on either side of it. So both of the environment, in this case, it is the environment of this hydrogen atom and this is the environment of this hydrogen atom. Both of those have different environments, and due to that difference in environment, it's going to have different del E value. Meaning this hydrogen atom needs a different amount of energy compared to this hydrogen atom. So to flip this hydrogen atom, what do you need? A different frequency of radio wave. Now to flip this hydrogen atom, you need another different frequency of radio wave. Since their energy required is different, based on their environment, which is why we can tell the type of the compound we have, type of the organic compound we have, based on which frequency of the radio wave it requires. Great. So the resonance frequency, depending on the environment of the hydrogen atom, is going to vary. And that frequency, that distinct frequency of each hydrogen atom in its own environment is going to give the exact Delhi value. This is why we see different peaks on an NMR spectra for the same compound. Great. Due to the difference in environment of the hydrogen atoms. Therefore, using the frequency or wavelength where the peak is seen, we can tell the environment of the hydrogen atom, which will tell us eventually the organic compound itself. Okay, so that was the process of what was happening. Now the reasoning of how the environment affects. How does the environment, the hydrogen atom environment, affect the energy needed to flip? Okay. Understand that up till now we were talking about isolated hydrogen atoms, meaning we are talking about a hydrogen atom that is isolated, and that means a specific del E value. However, in reality, in organic compounds, that hydrogen atom is not going to be isolated. It's going to be bonded with other atoms, right? Which is why the variation is seen in del E values, the amount of energy needed to flip the hydrogen atom. Okay. In reality, the hydrogen atom is bonded with different atoms, that is carbon, that is fluorine, that is nitrogen, anything, right? Therefore, the del E value is going to vary depending on the environment, right? So let's say you have an isolated hydrogen atom, that is an electron is moving around, is orbiting. So in this case, there is a certain amount of shielding. Now, if we compare it with, let's say, the CH bond, carbon-hydrogen bond, where both of these are almost equally electronegative, what's going to happen is these two shared electrons are going to be equally on either side of the bond. Both atoms are going to have 2 electrons, which is why for this hydrogen atom, what's going to happen is it's going to have greater shielding, greater amount of shielding from the electrons. And in case of one isolated hydrogen atom, less shielding is seen. Why? Only 1 electron. Great. Now, when the hydrogen is bonded with other atoms, it's going to share the electrons, which results in greater shielding. Now, how is this shielding affecting the del E value? What's going to happen is, due to the shielding of the electron, it's going to act against the applied magnetic field. So if your magnetic field is in this direction and you have an hydrogen atom over here, proton, and this is the atom, basically the nuclei, and if you have an electron going around it, it's going to shield it from the external magnetic field. So if you're applying 1 Tesla of magnetic field in its direction, due to the electron orbiting around, due to the greater density of the electron over here in the CH bond, there is greater shielding, meaning it's going to resist the magnetic field strength, the applied magnetic field strength, which is why in this case, in case of the CH bond, I need to apply greater energy. I need to increase the frequency of the radio wave such that a greater amount of energy reaches the nuclei of the hydrogen atom. Because due to the shielding, whatever I am providing, whatever magnetic field strength I'm applying, the entirety of it is not reaching the nuclei. So I need to increase my frequency of the radio wave so that the del E energy value, this energy change is met so that I can flip the spin. Therefore, due to the environment of the hydrogen atom, I need to apply different frequencies. In this case, where the hydrogen atom is isolated, I need to apply lower frequency because I need to meet a lower del E value. I need to apply less energy. In case of in case of the CH bond, 2 electrons, greater shielding. So to go beyond that shielding, I need to apply greater amount of energy. So I need to increase the frequency of the radio wave. Great. So, okay. So in case of a carbon-hydrogen bond, it gets shielded by 2 electrons. So since it's being shielded by 2 electrons, it now needs to have greater energy applied or greater frequency of radio wave applied towards it. Great. So what did we learn over here? We learned that when there is increased amount of shielding, we need to apply a greater amount of energy. We need to increase the frequency of the radio wave. Great. Now, one thing to note is in a, let's say, NMR machine, you can either keep the magnetic field constant and increase your radio wave, that is, increase the frequency of the radio wave and meet the energy requirement, or what you can do is keep the radio wave frequency constant and increase the magnetic field strength of the machine. So you can do either of the two things. Both are going to help you flip the nuclei of the hydrogen atom, flip the direction of the spin. Since both are forcing the nuclei to change its alignment. So, right now we are talking with respect to providing, we're keeping the magnetic field strength constant and we're applying greater amount of frequency of the radio wave, which in return does what? Provides the energy and turns the spin around. Great. So now if we compare two other bonds of hydrogen, that is CH bond, where the electronegatives are almost equal, shares the 2 electrons. In case of fluorine hydrogen, what happens is fluorine is the most electronegative atom. So it pulls both the electrons towards itself. That creates an electron deficient site for the hydrogen atom. So now the nuclei is free. What happens is you need less amount of energy right now, so less frequency of the radio wave to change the spin of the hydrogen atom, the hydrogen nuclei. So in this case, less frequency or less energy of the radio wave needed. In this case, greater energy, increased energy of the radio wave needed, that is greater frequency. Okay, so in the case of fluorine attached, we have less electrons, which is why less shielding, so lower energy needed, so lower frequency to flip the nuclei spinning direction. Okay. So in summary, what's happening? When we see that the hydrogen nuclei is flipped due to the radio wave, at that frequency we see a peak on the NMR spectra, which says that flipping has taken place. So now the important part, which is understanding how the graph works, right? So now we're going to understand the format of the NMR spectra graph. On the y-axis, what you're going to see is the absorption, that is how much flipping has taken place, that is how many hydrogen atoms or hydrogen nuclei have been flipped and changed the alignment. And on the x-axis, you have something unique, something different. Up till now, we talked about frequency of the radio wave, right? We said that at a certain frequency of the radio wave, we're going to see that the nuclei of the hydrogen atom has flipped. However, what we have on the x-axis is actually called chemical shift, or called, measured in parts per million. Now, what on earth does this mean? I'm going to explain it, don't worry. But before that, what we need to understand the x-axis, whatever it is, chemical shift, we need to understand something different. That is a reference point. So the reference is actually TMS, tetramethylsilane. What tetramethylsilane is, it's a reference point of how much energy or what frequency was needed to flip the hydrogen atoms of tetramethylsilane. In case of tetramethylsilane, what happens is, if you look at the bond over here, you have 4 CH3 bond, that is 4 methyl groups and 1 silicon. Note that in this case, the silicon has an electron donating effect. What that does is that increases the electron density. Notice, if I take this over here, one of the CH3, and put it over here, what I can observe is the electron density. Notice the electron density has increased due to the electron donating effect of silicon. So the electron density has increased. What does that mean? Greater amount of shielding. So what greater amount of shielding means? I need to provide greater amount of energy to the hydrogen nuclei. So on the, at this point where it's marked 0, this means over here I need to provide for tetramethylsilane, for the hydrogen atoms in tetramethylsilane, I need to provide the maximum amount of energy, the highest energy / magnetic field. As mentioned, you can change magnetic field or the energy. The highest amount of energy or magnetic field is needed for tetramethylsilane hydrogen atoms. Because in this case, we have an electron donating effect. The shielding has actually increased. So on 0, what this denotes is you need the maximum amount of magnetic field or maximum amount of energy to flip the hydrogen atoms over here, to overcome the shielding effect. So we're using a reference point called tetramethylsilane that gives a peak at 0, meaning at this frequency we have the nuclei of the tetramethylsilane, that is the nuclei of the hydrogen atoms, being flipped. At 0, flipping occurs for tetramethylsilane. Now, all the hydrogen in its compound are in the same environment, which is why we see one peak. Because all of these hydrogen atoms, notice, are in the same environment, are in symmetry, right? This CH3 is in the same environment, this compared to this CH3 as well. It's in the same environment again. So in general, all of these hydrogen atom bonds, or the hydrogen atom itself, is in the same environment, which is why we see one large peak for tetramethylsilane. Usually what happens is the amount of tetramethylsilane is less, so it's a small peak. But yeah, in general, what it means is, for tetramethylsilane, I need the maximum amount of energy or maximum amount of magnetic field to flip its hydrogen atoms. Great. So we understand this. Okay. Right. We need larger amount of energy to flip its spin. So what 0 denotes is maximum field or maximum frequency needed of the radio wave to flip a proton, that is of the TMS. Now, here is what parts per million or chemical shift really mean. You probably have been expecting that on the x-axis, frequency should be mentioned rather than chemical shift or anything. However, having frequency on the x-axis makes it confusing for different machines, meaning different machines have different magnetic field strength, which is why they need different frequencies. So to keep all machines on the same on the same metric, what they have done is created a ratio. Listen carefully. They've created a ratio of what amount of frequency I need in comparison to TMS. Because we know tetramethylsilane needs the maximum amount of possible energy to flip its hydrogen atom. It needs a large amount of energy. So compared to TMS, what amount of energy do I need for other hydrogen atoms? Let's say in this bond, for this hydrogen atom, this is one group, this is one group, and this is the same group. So these hydrogen atoms are in the same environment, whereas the white hydrogen atoms, all 6 of them are in the same environment, right? So what we're going to be observing is compared to TMS, how much energy do these hydrogen atoms need to be flipped? So it is a ratio. The x-axis is represented as a ratio against TMS. So what this basically means is, if we take an example that is an OH bond, to be clear, the OH bond is more electronegative, so it pulls the electrons towards itself, and it's going to create an area of less shielding for the hydrogen atom. Therefore, what does this mean? This hydrogen atom needs less energy. That means it's going to be in this direction. It needs less energy compared to TMS. So what we're going to see is it requires less magnetic field, call it, or less energy to be flipped, since less shielding. So let's say OH peak, the spectral peak for OH is seen as 4 parts per million, which is where? Over here. Let's say the peak for OH is seen over there. What does this mean? Parts per million means the amount of energy needed to flip the hydrogen atom in OH is 1 by millionth times less in frequency compared to tetramethylsilane. So it needs 1 by 4 million times less energy compared to tetramethylsilane. That is the meaning of parts per million or chemical shift. Compared to tetramethylsilane, how much less energy or frequency do you need? So that is what your ratio, this chemical shift ratio is telling you. And that is why you have chemical shift on the x-axis. That keeps it standard for all NMR machines to give you the chemical shift value, using which you can analyze what organic compound it is, what kind of hydrogen environment it is. Okay, so another term to remember is, since OH requires less frequency to be flipped, it is downfield. It is on the left side. It is on the left side, meaning it needs less energy, because 0 we know is the maximum amount of energy needed. So going left from it means downfield, less energy, right? Great. So going left means downfield compared to TMS, and upfield means being on the right hand side, meaning it needs a bit more energy. Let's say if there was a peak over here, I would say compared to the OH, the H in OH, this bond, this hydrogen atom environment, this hydrogen atom nuclei needs more energy, is comparatively upfield, right? Okay, so that is basically the meaning behind the measurement in the x-axis, parts per million, or chemical shift, what chemical shift means. Therefore, in summary, if there is more shielding, the peak is upfield, that is on the right hand side. If there is less shielding due to an electronegative atom being attached, which is pulling the electrons away from the hydrogen atom, in that case less shielding means it needs less energy which is why it's going to be downfield on the left-hand side. Now, on the y-axis, it's quite self-explanatory. Absorption, meaning how much of the radio wave frequency has been absorbed, meaning how much flipping has taken place. Therefore, let's say you have 6 hydrogen atoms in the same environment, that is going to have higher absorption because there are 6 of them. And in case you have 1 hydrogen atom or 2 hydrogen atoms in one same environment, that is going to have a lower peak, right? Lower peak, one will have a higher peak. Now, their position on the x-axis is actually going to depend on its environment. If the bond, let's say this OH bond, it's going to be this oxygen atom is going to pull the electron towards itself, so less shielding, which is why it's going to be on the left hand side. If it was simply a CH3 bond, in that case the H has a relatively higher electron density, which is why it would have been comparatively upfield. So that is how you understand where the position of the peak is going to be. Great. So that is how we analyze or understand the graph itself, the axis at least. Now, one thing to understand is, in case of analyzing organic compounds, any organic compound, an alcohol, aldehyde, ketone, whatever your organic compound is, to analyze it, you need to dissolve in a solvent. Now, let's say you're going to use a solvent called CHCl3 to dissolve, which is a common solvent to dissolve organic compounds. But in this case, you're not going to do that. Why are you not going to do that? Because the H in CHCl3 over here is going to cause its own peak on the NMR spectra. Now, you don't want that peak because that is going to mess up with the peaks of the organic compound itself. So you don't want the solvent to mess up the spectra of the organic compound, which is why you're going to substitute that with CdCl3, meaning you're going to add D2O, deuterium oxide, to this, to CHCl3. What happens then is the D from D2 deuterium oxide is going to replace the H, the hydrogen atom, from CHCl3. As a result, you're left with CdCl3, which is not going to cause a peak on your NMR spectra. Okay, right. So to make sure there is no peak due to the solvent itself, we are going to use deuterium oxide, so that it's going to replace, the deuterium is going to replace the hydrogen atom of the solvent, and at the end of the day, we are not going to see a peak due to the solvent. So we have a clean spectra graph. Great. Now we are going to analyze and understand different environments of an organic compound. So let's say we have butane, a very well-known compound. What happens over here is you have a line of symmetry over here. What does this mean? These few hydrogen atoms and these few hydrogen atoms are in the same chemical environment. Why? Because compared to this hydrogen atom, it is near to these few atoms. Even compared to these, this hydrogen atom, it is near to these atoms. So there is a symmetry between all of these hydrogen atoms. They're in a chemically similar environment. They're in symmetry along this line, which is why their behavior, magnetic behavior, is actually quite similar. I say quite because not exactly. We're going to see that why it's not exactly similar, but in general, it's actually similar. It's in a similar chemical environment, because if you see the 3D model of it, you're going to see all of them are equally distanced from each other, and for all these three atoms, there is this part of the compound, and even for these three hydrogen atom, there is this part of the compound, which is why their behavior remains same. Even for these few 4 hydrogen atoms, what you're going to see is their behavior is the same. Why? If we analyze these 2 hydrogen atoms, there is this and there is this. Now if I compare with this, you have again the same thing but on the left hand side and the same thing on the right hand side, which is why these 4 hydrogen atoms exhibit similar behavior. So now to understand how they're going to behave, the 6 hydrogen atoms on either end of the organic compound is in the same environment due to symmetry. Therefore, we're going to see a large peak due to 6 hydrogen atoms. We're going to see a large peak on the NMR spectra. Right. This height can sometimes be expressed as 6 on a low resolution NMR to describe 6 hydrogen atoms, meaning on a low resolution NMR, which basically means less amount of energy is applied. In that case, or the magnetic field strength is lower. So in that case, what you're going to see is due to the 6 hydrogen atom, there is going to be one peak. So if this is your graph, you're going to see one large peak due to the 6 hydrogen atoms and due to its similar chemical environment. Similarly for the 4 hydrogen atoms in the middle, is going to exhibit similar chemical properties, which is why it's also going to have a large peak but comparatively less. Right? So it's going to have a smaller peak, but it's going to have one peak on a low resolution NMR. Great. Fair enough. So now we understand how to identify different environment of hydrogen atoms. We see these and these are in similar environment, so these would give one peak. These are in the same again environment, so gives one peak. Now that is in case of low resolution NMR. However, if we increase the resolution, if we increase the magnetic field strength, we're going to observe another phenomena that is called splitting. What is it? That is called splitting. In case of high resolution NMR, which is applying a stronger magnetic field, we are going to see even the minute variation in the magnetic property of each of these hydrogen atom. What we are going to see is all of these hydrogen atom is actually going to be distracted or interfered by the neighboring hydrogen atoms, which is why we'll observe splitting. One peak will be split into several parts. Why is that? Due to the neighboring hydrogen atoms. These hydrogen atoms is going to have its own magnetic field, which is going to interfere with the neighboring hydrogen atoms, right? Okay. So due to the neighboring hydrogen atom, due to its spin, due to its magnetic field, it interferes with one of our peak and splits it into different parts. Now, how do I find the splitting pattern of the hydrogen atoms itself? Of, let's say, the CH3. How many parts will the CH3 on either side be split into? Initially, it was one peak on a low resolution NMR. In a high resolution NMR, how many parts will it be split into? So for that, we need to use a rule that is called N+1 rule, where N is the number of hydrogen atoms in your neighboring carbon atom or your neighboring atom. How many hydrogen atoms are in your adjacent carbon atom? That is for CH3. For your CH3, the adjacent carbon atom is this one, and connected to this, you have 2 hydrogen atoms. So you have 2 is equals to N. So if you apply the N+1 rule, 2 plus 1 is going to give you 3. So it's going to be split into 3 parts, right? So in our example again, since we were taking CH3, I said there are 2 neighboring hydrogen atoms. So N is going to be 2 and there's already one peak. This one basically means there is already one peak due to the CH3 behaving in a similar environment, and these 2 is going to interfere with it. So that 1 is going to be divided into 2 more parts. So it's going to be like this. So this 1 peak plus the interference of 2 hydrogen atom. So 1 plus 2, you get a triplet. So in our case, we get a triplet, which is right. So 2 plus 1, we get a 3, which is, we can see it is going to be splitted into a triplet with a relative intensity of 1:1:1, 1:2:1. So what that means is the height, that is relative intensity means the relative height of each of the peak, right? So the height of the middle one, I actually didn't draw it in proportion, but I'll explain. This height is twice the height of the smaller peak, right? So the height of the middle peak is going to be twice the height of the peak on either of its sides. So that is basically what relative intensity ratio means, right? And how to figure this out, I'm going to tell you later. So if we look at the splitting of CH2, oh, by the way, for CH3 over here, you have 2 hydrogen atoms. For this CH3 as well, you have 2 hydrogen atoms, which is why it's going to give you 2 plus 1. From either side that you calculate, it's going to be the same since it's symmetrical. So you can take either of the CH3 part. Anyways, for the CH2 part, what's going to happen is, notice these two CH2 are the same. So which adjacent carbon atom am I going to take? This one. This one. So that one has 3 different hydrogen atoms. So what we have is 1 peak due to CH2, 1 plus how many adjacent hydrogen atoms? 3. So 1 plus 3, 4. So we are going to have a quartet. What that means is we are going to have a separation of 4 parts. That is 1:3:3:1. So the peaks in the middle are going to be thrice as tall as the peaks on either side. So if I draw the quartet that is over here, notice this is the quartet, right? So you have this, then this, then this, and this. So this is 1 unit, this is 3 units. That is basically the meaning behind the intensity. Right. So if I plug both of these CH2 and CH3 on the absorption spectra, what we are going to see is the CH3 is upfilled compared to CH2. Why is that? CH3 has more electrons. Why is that? Because 3 hydrogen atoms, so greater electron density. For CH2, less electron density, 2 hydrogen atoms. That is why. So we see CH2 being broken down into 4 parts, quartet. Why? We saw it, 3 plus 1, 4 parts. Intensity 1:3:1. And for CH3, we saw it has its own 1 peak, and due to neighboring 2 hydrogen atom, 1 plus 3 parts, it's going to be divided into giving a quartet. Mind you, the CH3 peak is larger. Why? Because in the CH3 environment, you have 6 hydrogen atoms, and CH2 environment, you have 4 hydrogen atoms. So the CH2 peak will be lower, will be shorter. Great. Now, how to find the relative intensity? This ratio, how do you find out? Simple. It is basically based off of the Pascal's triangle. What is the Pascal's triangle? If you've forgotten, if you have 1 on top, bring down the 1 on either side, and the 1 plus 1 is going to give you 2. 1 plus 1, 2. Now bring down the 1 on either side. Now 1 plus 2 is going to give you 3. 1 plus 2 is going to give you 3. Now bring down the 1 down on either side again. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And bring down the 1, again 1. So for singlet, that is 1 part, it is going to give 1 peak. For triplet, 3 parts, that is going to give you 2:1. For quartet, that is going to give you 4 different parts, that is 1:3:3:1. For quintet, 5 parts, similar thing. Now for a doublet, that is not in the Pascal's triangle, unfortunately. It's going to be 1:1, that is same ratio, that is same height of the peak. When is it going to be doublet? So it's going to be when I'm going to show a table. So when there is one adjacent hydrogen atom and one peak for itself, so N is going to be 1. So 1 plus 1 is going to give you 2. In that case, you have a doublet. Great. So that is how we find the relative intensity, that ratio, using the Pascal's triangle. Right. So in case of CH2, what we got was 3 plus 1, 4. So we need 4 parts, which is this quartet. That is going to be this ratio. Okay. So what this basically means is this bit, I mean, you don't need to know, but in case of machines which have a higher magnetic field strength, that is, provides an even higher resolution of magnetic spectra, in that case, you're going to see even more peaks. That is, in the graph, you're going to see more than, let's say, in case of CH3, more than 3 peaks. That is due to the difference in magnetic behavior of the hydrogen atoms itself. So due to that, the splitting is going to happen even more, but it is going to be very minute, which is why you're not going to see in a low resolution NMR, since the peaks are going to overlap, and at the end of the day, you only get 3 peaks. But yeah, so basically there are even more peaks than what we calculate over here. But I mean, that's not important. That's a bit of an extra bit. Anyways, the important part though is understanding what kind of splitting we are going to have depending on the number of adjacent protons. So in summary, when you have zero adjacent proton, that is, you don't have any neighboring hydrogen atom, you're going to have a singlet, that is 1 peak. When you have one adjacent hydrogen atom, you're going to have a doublet. So N is 1, so 1 plus 1 is going to give you 2. So a 50-50 peak where the ratio is 1:1. In case you have 2 neighboring hydrogen atoms, a triplet, 1:2:1. So this is your peak. Now, in case of 3 adjacent protons, what you're going to see is a quartet. A quartet separated into 4 parts. In case of 4 neighboring hydrogen atoms, you're going to see a quintet, basically split into 5 parts. Okay, now some common singlet hydrogen atom environments is this is an alcohol, carboxylic acid, this is going to be aldehyde, this is going to be an amide. So in each of these cases, notice that you're going to have an H atom close to no other adjacent hydrogen atoms. In these cases, since no adjacent proton or hydrogen atoms, you're going to have a singlet, one single peak, right? One single peak. Because notice for alcohol, the neighboring atom is oxygen, similar to carboxylic acid, similar to aldehyde, no neighboring hydrogen atom. However, in case of amines, you can argue that there is a neighboring hydrogen atom that is over here, and due to that, you should see greater number of peaks, so there should be splitting. However, amine is actually a very interesting example where these hydrogen atoms actually readily exchange with the hydrogen atoms in the solvent, that is water. It exchanges readily with water, and as a result, what we see is, due to hydrogen atom not being in closely bonded to the nitrogen atom for a long period of time, the neighboring hydrogen atoms cannot feel the spin of these hydrogen atoms, since these exchange with the hydrogen atom in the solvent. As a result, what we see is there is only one long peak, that is a singlet, in case of amines. Due to these neighboring hydrogen atoms not being able to influence the peak, since they are readily exchanging with the solvent. That is not something you need to know, but in general, to remember, all these compounds are going to have a singlet, that is one peak. Now, the other thing in your syllabus is the use of deuterium oxide. Why is deuterium oxide used? That is, let's say you have organic compounds such as alcohol, carboxylic acid, or amine groups. What we do is we're going to add deuterium oxide, and that is going to replace the hydrogen atoms, these hydrogen atoms. And how that helps is it's going to form these compounds, and at the end of the day, what you're going to see is one of the peak, this singlet peak, is going to be removed from your NMR spectra. Because notice, if I take this alcohol example, you're going to get one peak due to this hydrogen environment, one peak due to this hydrogen environment, and one peak due to this hydrogen environment. So you're supposed to get 3 different peaks. Now there will be some amount of splitting, that is for this CH2, since the neighboring carbon atom has 3 hydrogen atoms, 3 plus 1 is going to form a quartet. For this carbon atom, it has 2 neighboring hydrogen atoms, so 2 plus 1, a triplet. So triplet, quartet, and a singlet, as seen above. So you are going to see 3 different peaks on the NMR spectra. However, the issue is, as I mentioned over here while explaining this, these are, where did it go? These are labile protons, meaning these hydrogen atoms actually readily change with the hydrogen atom in the solvent. So if you used water as the solvent, what would have happened is this hydrogen atom would exchange with the hydrogen atom of the water, and due to that exchange with the solvent, you're going to see that the peak on the NMR spectra is going to vary a lot. So the range of variation is actually very large, from 0.5 parts per million to 6 parts per million, 1 parts per million to 5 parts per million. So the variation is really large. So when you have an NMR spectra and you see that there is a peak on this end, but when you do it again, there's a peak on other side, you cannot predict what the peak is really of. So to omit that that issue, we're going to use deuterium oxide to replace the hydrogen atom with deuterium, so that we are going to remove a peak of the NMR spectra, so that we can better identify what the compound is. The other benefit is, if you have an OH functional group or NH functional group, adding deuterium oxide, small amounts of deuterium oxide, you're going to see the peak of the H, the hydrogen atom of the OH or NH is going to get removed. So when you see that a specific peak has been removed after adding deuterium oxide, you will know there was NH2 group or OH group. So that is how adding deuterium oxide helps. So in general, what we see is when we add deuterium oxide, a singlet is going to disappear from your NMR spectra graph. So that is how deuterium oxide helps in identifying the compound better and to remove this large range peak, which makes it easier to identify the organic compound. So that is basically it for proton NMR spectroscopy. Next up, we move on to carbon NMR spectroscopy. Okay, now for carbon NMR spectroscopy, as mentioned at the beginning of the video, it applies the same logic. In this case, we're just focusing on the nuclei of the carbon-13 atom, and that has its own spin, that has its own magnetic field, which interacts with the external magnetic field. As a result, we see peaks on the NMR spectra due to the flipping of the spin. So same logic applies over here, but there are a few differences. What are the differences? Let's see. In this case, in carbon-13, there is no splitting in carbon-13 NMR. Now, in case of hydrogen atom NMR, what we saw is the range of the spectra range from, let's say, 0 to 10 to 20 parts per million. In case of carbon-13 NMR spectroscopy, that range is far broader. That is going to range from, let's say, 0 to 200 to 250 to, I guess, maximum around 300. So carbon-13 NMR spectroscopy is not going to have splitting. A, B, it's not going to have a short range. It's going to have a large range, right? Okay. Now, even in case of carbon-13 splitting, the nuclei exhibit magnetic properties. So the process of how NMR works remain the same as mentioned and explained at the beginning of the video. Okay. So in case of carbon-13 NMR, we're going to see peaks for different carbon-13 environments. The same logic applies. So if we take an example, this is your example. If you have two CH3 bonds on either side of the carbon atom, you have one carbon atom in the middle and this double bonded O. So what you can see is this is the line of symmetry of two CH3 parts on either side. So these 6 hydrogen atoms, the white highlighted ones, are going to act similarly, are in the same chemical environment. This carbon atom is in the middle, has a different chemical environment since bond to the oxygen atom. So what we observe is in the absorption spectra, we're going to see one large peak that is near to 0. Again, even in this case, we use tetramethylselene as our example because remember, if I draw it again, these are your hydrogen, 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 and silicon. Even in this case, notice the silicon is actually has an electron donating effect, which is why the electron density of the carbon atom is really high, which is why you need maximum amount of energy to flip the nuclei of the carbon-13 atom. So even in this case, you use tetramethylselene. So again, since 6 hydrogen atoms in similar chemical environment, we see one large peak of CH3 in CH3 part of the molecule. Now you will see another peak that is for this one carbon atom, that is C being double bonded to oxygen atom, that is farther downfield and is going to be at around, let's say, 200. So that is going to give a shorter peak since one carbon atom. However, this is not directly proportional. The height is not directly proportional to the number of carbon atoms. But yes, the number of carbon atoms definitely impact the height of the peak. Anyways, you're going to see another peak in this case, that is of the solvent CdCl3. In CdCl3, notice there is carbon atom as well. This carbon atom that is bonded to deuterium. Remember, we change the hydrogen atom with deuterium. Why? So that we don't get a peak of hydrogen atom, right? However, in this case, we do have a carbon atom, right? Even in CdCl3, we do have a carbon atom. Even though it doesn't have a hydrogen atom, there is a carbon atom. So this carbon atom is going to have a small peak, since CdCl3 is the organic solvent we are using. So due to the carbon atom, we see a small peak over here, but you can neglect this. Okay, so we are having 3 peaks for this compound, 1 for the solvent, 2 for the carbon atoms in the compound itself. Now, how are these placed? Similar logic of shielding. Notice for these CH3, there is a greater density of electron that is due to the electrons of the hydrogen itself and the carbon's own electron. Now, one thing to notice is for the C double bonded to O, O is a electron withdrawing group. That is, it pulls the electron towards itself, right? So in that case, the carbon in the middle is going to have less electron density since it lost its electron to the oxygen atom, which is why less shielding, which is why less energy needed, therefore more downfield. In case of the ones on the side, again, yes, there is some amount of electron withdrawing effect of the oxygen atom. However, it's far less than the one in the middle, which is directly connected to the oxygen atom. So it is comparatively upfield. Right. So this is why you see one peak over here and one peak over here. And this is how you predict the peaks of carbon-13 NMR. And that is, in summary, how carbon-13 NMR and proton NMR spectroscopy work. So yeah, that's the end to spectroscopy. I might make videos on solving a few papers, but yeah, for now, this is it. Hopefully that this helped. Yeah, thank you for watching.